right, hi everyone. Really delighted to be here, and thank you so much for the invitation. This is such a fun event, and I'm seeing all of these friends, old friends that I haven't seen in a really long time, so it's really great to be here. So today I want to talk a little bit about some work that we've done in the lab, and I'll acknowledge the students, because this is all the students' work, on why interzonal airflow matters. How many people consider interzonal airflow when you're modeling your building or thinking about building performance? Is that part of your, okay, so we got a couple hands, that's great. Okay, so before I get into our talk for today, I just want to give a little bit of background. So I'm come from a 4-professor research group at the University of Toronto called the Hub for Advancing Buildings. We're quite an interdisciplinary group. We have indoor air quality expertise, smart buildings expertise, indoor microbiome, and I kind of work, as I mentioned, quite holistically in the MURB space, looking at that from a lot of different perspectives. Also just wanted to flag our relatively new Eng program with a building science emphasis. So we have now a dedicated program that really focuses on building science. And hot off the presses, we are now allowing or welcoming industry folks to come and audit some of our building science courses. So if this is of interest to you, definitely snap the QR code and or you can come and chat with me over the last hour as well. Okay. So I do want to acknowledge the students who've been working on this in this space. Most of the work that I'm going to present today is Kara Lazinski's Ph.D. work. She finished up a little while ago and is now a professor at the Carleton University. And some of the other key work that we're doing in this space related to airflow in MURBs is Justin Berquist, who's a current Ph.D. candidate. He's doing some really neat work looking at twin buildings, one centralized ventilation, one decentralized. I won't have time to get into that for the 20 minutes, but if that's of interest to you. And then Natalie, who just graduated and will be receiving her MASC degree next month. She was working on optimizing makeup air unit performance and basically how low can we go, because we tend to provide way more air than we need to in our central pressurized corridor system. So if any of those are of interest to you, I'm happy to chat about those later. But we're going to focus mostly on Kara's work today. So in terms of airflow in multi-unit residential buildings, this can be pretty complicated, but we really tend to focus almost exclusively on infiltration and exfiltration across the enclosure. But we've got a whole bunch of households that are separated by these interior partitions. And so we end up getting contaminant transfer, odor, smoke, moving between apartments. We also get a lot of uncontrolled airflow that's happening indirectly between apartments. So entering the common area spaces, maybe because that pressurized corridor system didn't work so well. And then we get stack effect that's driving those contaminants up through elevator shafts and stairwells and such. And that then re-enters units at the top of the building. So we get lots of neighbor cooking smells and smoke and things like that. So this is really, we're focused more on the interzonal piece here. And there's a lot of benefits to focusing on interzonal air tightness. There's energy efficiency benefits, which I'm going to show you, and that was really one of the key findings of Kara's work, was that there are real tangible energy benefits associated with getting interzonal air tightness right. I think intuitively there's going to be indoor air quality benefits. You know, we're seeing less contaminant transfer between households, and that's a good thing. It helps with our ventilation system efficiency. If we control or if we manage these uncontrolled leakage pathways, we can help air get to where it needs to go. We also have some other co-benefits related to acoustic separation. You know, good air tightness means you get less noise transfer, less pest transfer, and then of course smoke and fire separation. So lots of reasons why we really want to be paying attention to this. So the first thing I wanted to do is share some of the testing work that she did. I kind of joke, I feel like she probably never wants to see a blower door apparatus ever again in her life. She did what's called sequential pressure neutralization testing. Has anybody attempted that before? I'm sure there's some people in the room. And so the idea here is that rather than just doing a single blower door test on a single unit, we start with that, and then one by one we bring each of the adjacent zones up to that same test pressure. So essentially what that's doing is it's neutralizing the pressure across each of the 6 sides of the apartment, and that allows us to get a sense of where those leakage paths are, rather than a whole leakage value for the suite. And so what she did this in a number of different buildings and a number of different suites. On the far left-hand side, this is normally the test result we would get, so the average air leakage for the entire unit. But she uniquely was able to separate this out into those different partitions. So floor to ceiling, we're doing pretty well. Unit to unit, also pretty well. The real weak link is that fifth one on. Sorry, I know I'm not supposed to go in front of the screen, but like there. So we see that that's the real weak link. So while it looks like the suite is performing really well, it's not until we break this down by partition that you start to see the weaknesses. And what's interesting, even when you separate this out by wall construction type, we still see those significant differences. Now, if we chop and change this a little bit, within her sample, there were EnerPHit and Passive House certified buildings. And we see similar patterns, right? So we're just not paying attention to those suite to corridor walls. It doesn't really matter whether you're certified or a base code building. Those all tend to exceed our interior airtightness requirements. And this is because fundamentally the way we build these walls are different. Our unit-to-unit walls have a lot more redundancy in them, and that just naturally is going to lead to better airtightness compared to our unit-to-corridor walls. And so to me, this seems like a relatively easy fix. I should note that none of these values actually include the air leakage of the suite door. So these are actually far leakier than what we see here. But that can be solved with weather stripping pretty simply and cheaply. So the key takeaways from her field work were really that the current compartmentalization requirements are actually really easy to achieve. Even if we're not trying for some of the ASHRAE target or the LEED target, you pretty much meet them anyway based on how we currently construct buildings. But doing that single fan test kind of hides that variability. And so we still have these weak links, which can lead to in-service performance issues. And then the other takeaway, I think, for this crowd is that there's really no difference between conventional and passive house when we look at that interzonal partition. So she took all of that wonderful field data and used that to build some models so that we could start to explore what are the impacts of changing specific interzonal partitions. And so there's a lot here. I'll just, at a high level, she took a low-rise building, 4-story, mid-rise, and a high-ish rise, 20-story building, and used the data from her fieldwork to represent the different interior partitions. So we were separately adjusting enclosures, separately adjusting interior partitions, so the walls between suites, between the corridors, and then separately adjusting things like elevator doors and stairwell doors. So that way we could do parametric analysis and understand if we turn this one lever, how does that impact our performance? And then the main outputs that we were interested in were energy. So does this have energy benefits or not? And then to what degree does this impact indoor air quality? And I should say indoor air quality is such a broad term. What I'm referring to specifically is interzonal contamination transfer. Okay, so let's take a look. And that resulted in many simulation cases. And she, just for those that are interested, she used a coupled simulation between Energy Plus and Contam. Does anyone use Energy Plus in the room? No? Okay. Some people. Okay, so building performance simulation typically used for energy modeling, and then Contam is a transport contaminant software, and then there's a way of like coupling them. So with each time step, they're feeding information back and forth to one another. So that was the approach that she took. All right, and so if we look at the results, again, a lot going on here. This is the sort of base model, the floor plan of the model that she used. So she basically seeded one zone with a contaminant, and what we were doing was looking to see where that contaminant went throughout the building. And so if you imagine on the left here, we've kind of got this building that's opened up like a book. So we've got our stairwell, corridor, and elevators in the middle, and then the apartments on either side. So this zone is just doing a lot, emitting a lot of contaminants. And then the colors indicate the intensity of those contaminants as they're moving through those different zones. So they're moving, along the corridor into the adjacent suites, vertically through that suite, floor to ceiling connection. And then probably the most effective contaminant transfer is indirectly through those elevator shafts and stairwells. So we really get that effective vertical connection between the floors. And so if we look at this as kind of a base case, so everything's fairly typical in terms of airtightness. When I mean typical, based on the fieldwork that she did, and what do they have? Kind of the different delineations between loose, typical, and tight. And so then the first thing she did was tighten up the building envelope. Oh, all the problems are solved, right? No contaminant transfer. Okay, we're done. What about window operation? These are residential buildings. People open their windows all the time, 365 days a year. The number of times that I'm biking around Toronto and I see apartment buildings with their windows wide open. So yes, it is possible to achieve this level of enclosure airtightness, and that's a really important part of the Passive House certification. But in a residential context, it's not something that we can rely on consistently. And so, so the next thing she did was, I'll just take you through some of these cases. So we have our base case that we looked at before, a typical building envelope or tight that you saw on the previous slide. The next one is just tightening up the suite partitions. So the suite to suite walls and the suite to corridor walls, which is a little bit of an improvement from the base case. But then if you look over on the right, that's just tightening the elevator doors and the stairwell doors. So loose enclosure, loose interior partitions. And you'll see that it's very similar to if we had our tight enclosure, but a lot more robust, because now people can open their windows, because the people open their windows for lots of reasons. It might be temperature control. It might be they're not getting the ventilation that they require. It might be they want an acoustic connection to the outside, hearing the birds chirp. Who knows? Occupants do wacky things, as we've seen. So what this allows us to do is achieve that the same benefits in terms of reducing that interzonal cross-contamination, but adding that robustness. So people can still do whatever they want in their suite. It just doesn't affect what happens in the rest of the building. Okay, so what does this all mean for energy? There's a lot going on here, so I'll just get you oriented. So on the y-axis here, vertically, we've got space conditioning energy use intensity. So this is the energy that we use for heating or cooling in the building. I forgot to mention this, but in the modeling, she modeled 3 different types of ventilation systems. So one, a pressurized corridor system, which I'm sure many of you are familiar with it, but for those that aren't, this means we have a central makeup air unit on the roof that is pushing air down through vertical ducts into the corridors on each floor. The idea is that you're positively pressurizing those corridors so that air magically works its way under the door undercuts of the suite and perfectly ventilates the suite all the time, no matter what the outdoor conditions, right? I know, it's magic, it's fantastic. So the middle one is a direct ducted system. So that means you'll have a central ventilation system similar to the first one, but instead of relying on this very robust pressurized corridor system, you're ducting that air directly to the suites. And then on the right-hand side, we've got in-suite HRVs. So that means each unit, each suite, has its own dedicated balanced supply of outdoor air. And so we've got those cases grouped. And then each one of those, we have the 4 cases. So the base case that I showed you, everything's typical or loose. Sorry, now I can't remember. Might be loose. Tightening up the building enclosure only is the first or the second bar over. Tightening up just the interior partitions, and then tightening up just the shafts, so the elevator and the stairwell. So if we look at the energy savings associated with each of these cases, we can see that in all cases, just addressing the shaft airtightness actually has the biggest reduction, more so than the enclosure. And that's a really important piece. So we've not only, from an indoor air quality perspective or from a contaminant transfer perspective, really improved that with our shaft airtightness, we also see really good energy benefits as well. And these are significant, particularly with the in-suite HRBs, so almost a quarter, or almost 25% reduction. Okay, this is my favorite plot in her thesis, so bear with me while I explain this. But this is ultimately, when we started this project, what we wanted to get to. So on the y-axis here, you basically got the fraction of air that's coming from somewhere else. We do not want that. We want ventilation air. We do not want our neighbor's air or the person down on the first floor's air. So this is all of our own air, and this is, say, 25% of our air is coming from a collection of other suites in the building. On the x-axis, we've got space conditioning energy use intensity. So basically, we want to be as far to the left and as far down as possible. That's good. Just to orient you with the legend, so the pressurized corridor systems are in triangles, the HRVs circles, and the direct ducted, and then there's a whole bunch of different cases. That's too much to digest, so let me just take you through a couple of examples. So with the pressurized corridor system, when we tighten the building envelope, we get both the reduction in, as expected, and as you saw, reducing the energy use intensity and improving that, or reducing that interzonal cross-contamination. Just doing the vertical shafts in that same system has slightly better energy performance, slightly worse on the indoor air quality, but still better than the base case. Now, if we jump down to just tightening up the interior partitions, and then tightening both the interior partitions and the vertical shafts, that's really where we start to see some pretty big benefits. And then if we just tighten everything, we're doing great. But remember, so all of those purple ones, the solid purple, assume that all of the windows and doors are closed properly. So that's really the best theoretical case. We're really never going to see that in reality. And then HRVs and things. If you are interested in exploring this further, we have a little 2 or 3 page industry bulletin. I'm happy to share that with all of you. And then you can kind of go through this and explore your own cases for buildings that you might be contemplating retrofits for or design alternatives. So the main takeaway here is that stack effect, or those vertical connections, are really the main drivers of interzonal cross-contamination. That's really what we need to control, and we can do that well through elevator doors and through stairwell, or sealing off those stairwell doors. While the building enclosure or building envelope airtightness can be really effective, it really depends on what's happening in service. So when windows are opening, we just don't see that robustness of that solution. And so what we're hoping this community will start to adopt is those compartmentalization strategies, or addressing that interzonal airtightness in tandem with enclosure upgrades. We're not saying don't do enclosure upgrades, but make sure that you're addressing that interzonal airtightness to really get maximum value and benefit out of that. So the main takeaways, I hope I've shown you that interzonal airtightness really matters, and we need to be paying attention to that for lots of different reasons. Energy, air quality, sound transmission, pest transmission. There's so many co-benefits associated with this, and we're literally talking about weather stripping. Elevator doors are a little trickier, vestibules and things like that, but these are relatively small changes. We really need to start addressing this in tall buildings. The taller the building, the more this matters. The taller the building, the more this matters. So we did 20 stories. We're currently working on 40, 60, and 80-story models because we do have a lot of high-rise buildings in the city to really demonstrate how that energy saving scales. Related to Natalie's work, who I mentioned at the outset, the other thing to kind of keep in the back of your mind is I mentioned we often oversupply air to the corridors. Even when we have in-suite HRVs, we were working with a building recently, they were supplying 30 CFM per door, which is what you would need to basically ventilate the entire suite. All we're ventilating is this little corridor. So thinking about how much air, this is another huge potential for energy savings, is dialing that down and making sure you have good compartmentalization so that pressurization is easier to maintain. So the next steps for us, I mentioned we're doing this further modeling. I recognize that no one in this room is going to do this coupled Contam Energy Plus simulation. So what we're doing is we're developing a surrogate model, which will feed into ideally a web-based tool for designers to just give us some basic metadata about your building height, basic leakage characteristics, and then you can use this tool to get an estimate of EUI reductions and reductions in cross-contamination. So that's something we're going to be working with over the next 12 to 18 months. So maybe I'll come back and I'll share the tool at a couple of events from now. And then the other thing we're doing, I've been trying to talk to elevator manufacturers and talk to folks in the space, because in my mind, that's the real weak link. Stairwell doors are really, really easy and cheap to deal with. Elevator doors are not. And so if anybody wants to chat with me about elevator doors and how to deal with that, I'd be happy to do so. So I will leave it there. Please get in touch if you would like to see any of this information. I'm, of course, happy to share it. And thank you.